Hey guys, today we're going to be doing 11-3. So here are our objectives for today. We're going to be able to interpret shapes of data displays representing different types of data distributions. Okay, so this is 11-3, interpreting the shapes of data displays. So here we are, first example. The histograms show the weights of all of the dogs entered in two different categories in the dog show. Consider each data set. What inferences can we make based on the shape of the data? Okay, so looking at this first example right here, the one in the orange, we see n equals 95. That tells us our sample size. Okay, this means we have 95 dogs we looked at. Okay, frequency is here on the y-axis, weight is here on the x-axis. Okay, so we're looking at a histogram of their weights. Okay, so we've got 10 dogs that are 10 to 19 pounds, 20 that are 20 to 29 pounds, 25 that are in between 30 and 39 pounds, okay, and so on. Okay, notice this data looks fairly symmetrical. Okay, then if I look at the blue graph, okay, n equals 100, so our sample size is 100. So we're looking at almost the same number of dogs. Okay, we have frequency again here on the y-axis, weight here on the x. So we've got 20 dogs here that are 0 to 9 pounds, 30 that are 10 to 19, 20 that are between 20 and 29 pounds, and so on. You notice this one doesn't look as symmetrical as the orange graph. So let's see what that means. Okay, so let's just talk about the orange right now. The histogram is symmetric, okay, and shows the data are evenly distributed about the center. Okay, it's pretty symmetric. So when we have a symmetric graph, it means the mean and median of the data are equal or almost equal. Okay, so they're pretty close to each other. So based on this data, we can infer that most of the dogs in the category weigh between 30 and 59 pounds. Okay, that's where, yeah, we're right about in there. I gotta get a sneeze. Sorry. Okay, so moving on to the blue graph. Okay, we noticed again this was not symmetrical. We say this histogram shows the data are skewed right. Okay, to me, I always want to say it's skewed left because we're gathered more on the left. But when we're talking about skew, we look at the tail. Okay, notice how it's kind of flattening out down here. Yeah, that's what I call the tail. So it's called skewed right because the tail is to the right. When we're skewed right, this means that the mean is greater than the median. Okay, so based on this data, we can infer that most of the dogs in this category weigh less than 30 pounds. Okay, so here on the next slide, I have just drawn a quick picture of each of the skewed graphs and what it means in regards to their mean and median. So my first example here, the data is symmetrical. This means that the mean and median are equal or nearly equal. Okay, we call this a bell curve, nice and pretty. Okay, my next type of graph, this data is skewed to the left. Again, notice because the tail is to the left. When it's skewed to the left, that means the mean is less than the median. And then finally, my last graph, this data is skewed to the right. Again, notice my tail here is to the right. So when this happens, the mean is greater than the median. Right? So keep that in mind. So let's look at a third try it problem. So suppose a third category of dogs has a mean of 40 pounds and a median of 32 pounds. What can we infer about the shape of the histogram for the dogs in this category? Okay, so my mean is greater than the median. Okay, what does that mean? Well, if you can't remember, come back over here. The mean is greater than the median, so that means the data is skewed right. Okay, the data is skewed right. So if you want to think a quick sketch, it looks something like this. Okay, the tail is going to the right. In example 2, we're going to interpret the shape of a skewed data display. So customers of the bagel shop complained that some bagels weigh less than the amount on the label. Quality control managers randomly sampled 30 bagels and weighed them. Based on this sample is a change in the process for making bagels warranted. So the label says, okay, bagel has to be 90 grams. So some people are crazy and they're weighing their bagels and they're not going to be 90 grams. So the person in charge randomly picks 30 bagels. Okay, he picks one here, one there. Okay, he gets 30 of them. Then he weighs them all. He finds that the mean weight of the 30 bagels is 87.7 grams, but the median weight is 30. Okay, what do you guys think? Do you think he needs to change this process? Well, looking at this graph, okay, notice we are skewed left. Okay, my tail's over here to the left. This is common when the mean of the data set is less than the median. Okay, and we say that the mean is less than the median. Because the mean of the sample is less than the advertised weight, right? Quality control manager wants to recommend some changes. However, we got to think about our sample size. If you're thinking about a bagel making company, is 30 bagels a lot of bagels? Absolutely not. Okay, so because the sample consists of only 30 bagels, the manager decides to generate another random sample. Okay, you're not. This is what statisticians do, which is kind of fun. You're not happy with your sample, go get another sample. Your results are going to change. Okay, and a lot of times companies do this until they get the results they want. So they can say, hey, I've collected this data that supports this. Okay, so that's the fun part about stats. A lot of people say statistics lie. Well, you can kind of make them do whatever you want to do. And you can keep changing your data until you find something that you like. So that's kind of something I like about stats because it's just, there's so many ways you can do it and it changes all the time and you can make the numbers support whatever you want them to. Okay, so this sample says, we have something that's wrong. We need to change some things. Well, let's try another random 30 bagels and see what happens. Okay. I'm going to skip that one. Okay, so now customers of a bagel shop. So same thing, okay, except now we have a new sample. Okay, my new sample's here on the left. This time when I pick 30 bagels, I get the mean weight is 97.7 grams. All right, now I'm over what I wanted. Okay, and the medium weight is 90. Okay, and this over here on the right is the sample we just looked at. Okay, the mean was 87, the median was 90. So notice my new sample, now I'm skewed to the right. Okay, originally we were skewed left. So the shape of this data is skewed right. This often occurs when the mean of the data is greater than the median. So in this example, the mean is greater than the advertised weight and greater than the mean weight from the first sample. Okay, so now the sample is saying, oh no, we're doing too much to our bagels. So based only on this sample, again, the manager could recommend some changes. However, this sample gives opposite results from the first sample. Okay, so now I've got two different samples telling me two totally different things. First one's telling me my bagels are too light. Now they're telling me they're too heavy. So I have conflicting findings about the mean weights of the bagels. So what do you think we should do? Okay, we already talked about this, so I'll skip that. So I'm going to generate a third sample now that contains twice as many data points. So instead of only picking 30 bagels, this time I'm going to pick 60. Okay, and we usually do a larger sample size. Okay, and when you pick more data, the more accurate you're going to be. So a histogram that represents this third larger sample is below. Based on this sample, is there a change in the process? Is a change in the process for making bagels warranted? Okay, should we make a change based on this sample? Okay, well, this time we have 60 bagels. And oh, look, it's symmetrical. We both get the mean and the median are both 90 grams. So what do you think? Should I change my process? So the data points exist symmetrically distributed. In the sample, the mean and the median are the same. Based on this larger sample, the quality control manager determines that the process of making bagels does not need to change, okay, because the data are centered around the advertised weight of 90 grams. Okay, so finally got the data I wanted. I can bring this back to my boss and say, nah, we don't need to make a change. Here's my data to prove it. Okay, so now let's talk about adding maybe another 10 bagels. Okay, so this time I'm looking at the original 60 I picked plus another 10, so my total will be 70. Okay, 5 of the bagels are 78 grams and 5 of the bagels are 106 grams. How would that affect the mean and the median? Well, We know the mean and the median are both 90. Adding 5 data values that are less than the median and 5 data values that are greater than the median, is that going to change my median? Okay, if I have a median here in the 90, I add 5 up here, 5 down here, is that going to affect what's in the middle? Absolutely not. So these 10 values does not change my median. Okay, so let's talk about the mean now. 78 is 12 less than 90. 106 is 16 greater than 90. Is that going to change my mean? Absolutely. Adding the new values would affect the mean by making it greater. Okay, I'm adding more to the bigger side of 90. Therefore, my mean is going to increase. Okay, and they actually calculated the new mean would be at about 90.3 grams. Okay, so picking more is going to change my statistics. All right, so let's look at example 5 now, comparing the shapes. So this is actually something very interesting, something you should think about when you're getting ready to start looking at jobs. Jennifer's considering job offers from 3 different school districts. The histograms show the salary ranges for similar positions in each school district. What do the shapes of the data tell Jennifer about the teacher salaries in each district? So school district 101, okay, that is symmetrical, okay, nice and pretty. We like symmetrical. Our mean and our median are about the same. School district 201, let's scoot to the right, okay? And then school district 301, I'm skewed to the left. Let's think about these. Okay, so school district 101, they tell us that the mean is 52,000 and the median is 53,000. Okay, school district 201, our mean is 48,000, the median is 42. School district 301, our mean is 65 and the median is 70. Based on just that, I don't like the look of school district 201. I want to be where the money is. Okay, so the data from teachers in similar positions in school district 101 have salaries that center around the median. This indicates that the salaries of the teachers are fairly evenly distributed. Okay, we like when it's evenly distributed. Okay, going back to 201, the data from teachers in district 201 is skewed right. Most of the teachers in that district have salaries that are lower than the mean. This indicates that there are only a few teachers that make a higher salary. Okay, you got to be one of the top ones to get that kind of money. To me, that doesn't seem quite fair. So moving on to 301, the data from teachers in school district 301 is skewed left. Most of the teachers in similar positions have salaries that are higher than the mean. This indicates that there are more teachers that make a higher salary. So, which one do you like better? Again, I would cross out 201. So if Jennifer's starting salary is the same at each school district, she should strongly consider school district 101 or 301. Based on the data here, these districts have more potential for Jennifer to advance her salary. Okay, so it'd be your choice there. And of course, if I was looking for a job, I would look at other factors besides just the money. I would look at class size, I would look at what I would have to teach, that kind of stuff. Okay, so now suppose a 4th school district offers Jennifer a job. School district 401 has a mean salary of 57,000 and a median salary of 49. Do you think she should consider accepting the job offer of school district 401? Well, my mean is greater than the median. This indicates that the teacher's salary in school district 401 are skewed right. The mean is likely higher than some of the other school districts because there are a couple of teachers at the high end of the salary scale. However, half of the teachers earn below 49,000. So do you think she should go there? Probably not. School district 101 or 301 still look better. That's what I have for 11.3. 11.3 is not so much writing out math problems like we're used to. It's more thinking through what the data is telling you. Okay, this is what statisticians do. So let's talk about the summary real quick. The shape of a data display reveals a lot about the data set. In a symmetric data display, the data points are evenly spread to either side. The mean is equal or close to the median. When the data is skewed, the data points are unevenly spread on either side of the center, which we call the median. A data display can be skewed right or skewed left. Okay, that means my mean and my median definitely not equal. Okay, so this data set here is symmetric. There are a similar number of data points greater than and less than the mean. Okay, here's what a dot plot or yeah, a dot plot looks like when it's skewed. Okay, one family of 5 pets skewed the data to the right. The very small sample difference size makes inferences unreliable. Okay, homework tonight, not very many problems. You're going to be on page 485. You're doing problems 9, 13 through 17. As always, please let me know if you have any questions. Hope you guys have a great day.